In terms of this lovely warm-up problem, this is just to kind of get us in the mood thinking about trig. So in general, usually a lot of people, when you hear trig and sine, cosine, tangent, there's this little acronym, SOHCAHTOA, that people use. Doesn't mean that you have to, but sine of a given angle should be the opposite side over the adjacent side. So looking at our triangle, I've given us theta. This 5, because it's on the side that's touching that angle and not the hypotenuse, we call this the adjacent side. The side that is not touching the angle and is not the hypotenuse, we call the opposite side. So on my triangle, I actually didn't give us the opposite side, didn't give us the value. So we're gonna have to start by figuring out what the height is on that opposite side. And it means I'm gonna go ahead and use the Pythagorean theorem. And to get this missing side of the triangle, I'll just label it something. I'm gonna label it y just because it's kind of a height here. And I know that from the Pythagorean theorem, I'm going to end up with 5 squared plus y squared would be equal to the square root of 41 squared. That's true anytime I've got a right triangle. Figuring this out, 5 squared, I've got 25 plus y squared has to be equal to square root of 41 squared is 41. So y squared is going to have to be 16. No, yes. Did I get that right? 41 minus 25?
Yes.
I think it's 16, which means technically y could be positive or negative 4. However, here, it doesn't make sense for us to have a height of negative 4. So our height here, our y, is going to be a positive 4. And so now thinking back to sine should be the length of our opposite side over the length of our hypotenuse. So on a right triangle, the hypotenuse is always the side that is not making the 90-degree angle. So my hypotenuse here is square root of 41. And that opposite side is 4. Cosine for this picture, cosine is my adjacent side over the hypotenuse. So I'm looking at this adjacent side of 5 over the hypotenuse of square root of 41. Tangent is my opposite side over the adjacent side. So tangent would be 4/5. Basic idea if I'm trying to solve a trig equation is I want to get the trig piece by itself, or if there are multiple trig pieces, I want to get each of them by themselves. So in this case, that sine of x, I'm going to want to isolate that whole thing. So I'm subtracting 1 and dividing by 2, which leaves me with sine of x is equal to negative 1/2. At this point, we're not reaching for a calculator. We're thinking to ourselves, hey, sine of what angle is equal to negative 1/2? And there's 2 pieces to this. One, that negative is telling me something about what quadrant my answer is in. And this 1/2 is telling me which special angle to go look for. Regardless of how you memorized your special trig angles, I'm just going to show you the way that I have them memorized, and that is I draw triangles. So people are already giving me some answers, and that's awesome. I'm going to attack the special angle first and then come back for the quadrant piece of this. So if I'm looking for sine to be 1/2, there are 2 triangles that I work with. One is an equilateral triangle. And if I called this side 2, then when I cut it in half, this side would be a 1. And using Pythagorean theorem, like we did for that warm-up problem, we could come up with this side is the square root of 3. Because it's an equilateral triangle, I know all interior angles are 60 degrees or pi over 3. That also means that when I cut that angle in half, or I bisect the angle, then the angle up here would be pi over 6. So if I need sine to be equal to 1/2, I'm looking for the angle where the opposite side is 1 and the hypotenuse is 2. And the 1 is opposite of pi over 6. So I know that my reference angle is pi over 6. So I'm doing something with a pi over 6. But I need to take into account the fact that it's negative. There's kind of a little acronym that sometimes we use. All students take calculus. I learned it as another stupid trig class, but then when I got to Davis, everybody was saying all students take calculus. I was like, oh, okay. So yeah, all students take calculus. I need sine to be negative. This right here tells me which of the sine, cosine, and tangent functions are positive in which quadrants. The other way to think about this is sine, because it's the opposite side over the hypotenuse on a unit circle, that corresponds to sine goes with the y values. So if I'm thinking about which quadrants have negative y values, we're looking at quadrants 3 and 4. Now, I know that I need to place pi over 6 in quadrants 3 and 4 so that I'm dealing with that negative. And the way that I place that into quadrants 3 and 4 is I look at thinking about my unit circle. Here's 0 and here's pi. And if I kept going, that's 2 pi. Since my reference angle is pi over 6, I want to rewrite the pi and 2 pi in reference to sixths. So pi is 6 sixths, and 2 pi is actually 12 sixths. By rewriting those in terms of 6, in terms of having the same denominator as my reference angle, now I can come in and say, well, if I have to get into quadrant 3, then I'm starting at 6 pi over 6 and going 1 more. So now I'm at 7 pi over 6. And if I need to take my reference angle of pi over 6 and place that into the 4th quadrant, all the way around, put me at 12 pi over 6, and I need to back off 1 to be at 11 pi over 6. And those would be my 2 answers. Looking at this trig equation, couple of things. First is a notation issue. So this notation of cosine with the 2 here and then x, we read as cosine squared x. What that actually means is that we have cosine of x and the whole thing is squared. I don't know why. Someone chose this notation to mean this. So looking at that, if the cosine of x is the thing that I'm trying to isolate by itself, I'm going to start by trying to factor this because it's quadratic with respect to cosine of x. So that 2 cosine squared x minus 3 cosine x plus 1, I'm hoping that this factors. And if I'm thinking about it factoring, there's only one way to get 1s. And there's only one way to get a 2 cosine squared x. I need a 2 cosine x and another cosine x. So now I just have to figure out the signs in terms of factoring that to end up with a negative 3 cosine x. And it looks like they'll both have to be negative. Now I really have 2 questions to solve for. Either this one is telling me that cosine of x would have to be equal to 1, And this is telling me that cosine of x would have to be equal to positive 1/2. Once I've kind of isolated those trig functions, now I'm back to thinking about unit circles, special triangles, special angles. What are those angles that give us these values? As another option in terms of how to memorize the special angles, especially when we're looking at values of 0, 1, and -1, another option we have is to think about what the graph of cosine of x looks like. If I think about a graph of cosine of x, it starts up here at 1, and it returns to 1 after one period or one full cycle, which brings me to 2 pi. The lowest value that cosine ever takes on is -1, and that happens right in the middle at pi, and cosine is equal to 0 at pi over 2 and 3 pi over 2. If I use this graph, then I know the angle where cosine is equal to 1 is 0 or 2 pi, but thinking back to the way I phrased the question, we're only going to include the 0 and not the 2 pi. So one of our possible answers here is that x is equal to 0. Our other answers are going to come from over here, from cosine of x being equal to 1/2. Even though there isn't a minus sign on this, there is an invisible plus sign here, and that is going to tell me which 2 quadrants I'm working in. And the 1/2 is again going to be back to our reference angle. So I needed that triangle again. I've got my equilateral triangle. If I label this side 2, then when I cut it in half, this side will be 1, and that height will be the square root of 3. Because it's an equilateral triangle, all of those interior angles are going to be pi over 3 or 60 degrees. When I bisect the angle at the top would be pi over 6. If I'm looking for cosine to be equal to 1/2, then I need the adjacent over the hypotenuse side to be equal to 1/2. And the angle we're looking for, that reference angle, is pi over 3. Now we're going to address the quadrant issue. If cosine is going to be positive, that tells me that I'm looking for the quadrants where the x values are positive, or I can also think about that all students take calculus. Cosine is positive in that 4th quadrant, and everybody's positive in the 1st quadrant. So I know I'm looking for values in the 1st and 4th quadrant. 1st quadrant's already done for us, so now we just have to figure out that 4th quadrant. And I'm going to use the same trick that I did last time. If I think about that unit circle going all the way around, I would be at 2 pi, but I want to write that in reference to the same denominator from my reference angle. So instead of thinking about this as 2 pi, I can multiply the top and the bottom by 3 to get 6 pi over 3. Then once I know where that reference is, then I'm backing off 1 to get into the 4th quadrant, and I'm going to end up at 5 pi over 3. So these are my solutions for this equation. Be on a nice unit circle that it's worth talking about a little bit. So first of all, when we say unit circle, that means we're making the radius of our circle equal to 1, so that no matter where I draw a radius, it's always going to be 1. In terms of trig, our angles start here and move counterclockwise around the circle. So we could call this 0 degrees or 0 radians. If we go all the way around the circle, we've gone 360 degrees. But because calculus only works in radians, we usually want to think about that as 2 pi radians. So halfway around the circle is pi radians, and half of that again is pi over 2 or pi by 2 radians. Down here, I'm halfway between pi and 2 pi. So down here is 3 pi over 2. So we certainly need to know what the trig, we need to be able to evaluate our trig functions for sure at each of those 4 points. Now, at any of those 4 points, I can't really draw a triangle, so instead we think about them as coordinates. So here, the coordinate, again, remembering that it's a unit circle, so the radius anywhere I put it is 1. So that coordinate is 1, 0. The coordinate up here, our x value is 0, but our y value is 1. So I'm at 0, 1. Out here, because we're to the left of the y-axis, I'm looking at -1, 0. And here, because I'm below the x-axis, I'm looking at 0, -1. When I mentioned that cosine goes with the x values and sine goes with the y values, that's coming from thinking about placing a generic triangle somewhere on this unit circle. So if I put a generic triangle in here, and I know that the radius is 1, and I think about this having an x, y coordinate, that means the height of this triangle we could call y, and the base of that triangle I could call x. So if I put my theta right here, and we think about cosine of theta, well, cosine of theta is the adjacent side over the hypotenuse, so that's going to be x over 1, or really just our x value. In terms of sine of theta is going to be my opposite side over the hypotenuse, so that's going to be y over 1, or just y. And tangent of theta is going to be my opposite over my adjacent side, or y over x. So on the unit circle, specifically because that radius is 1, when we draw out the unit circle, we can read off the cosine, sine, and tangent by looking at the x and y coordinates. Let's make myself some space in here. Now I mentioned quadrants, and we label our quadrants in the counterclockwise direction as we're building our angles out. So this is the first quadrant, the second quadrant, the third quadrant, and the fourth quadrant. And usually we write them with Roman numerals, but I'm being lazy today. So 1, 2, 3, 4 in terms of the quadrants. If we memorize values in the first quadrant, then we know those values in all of the other quadrants by symmetry. So if you feel like you need to memorize a unit circle, if that's the choice you're going to make for the special trig angles, then we want to make sure that we're doing that in the first quadrant. So here is an angle of 0, and here's an angle of pi over 2. So bisecting that angle, or right in the middle, that's an angle of pi over 4. Well, if I know that that side is 1, and I'm going to get rid of my quadrant numbers just so that they aren't confusing to us. So if I know that this side is 1, and that's an angle of 45 degrees, then each of these sides have to be the square root of 2. So if I were to label this coordinate for an angle of pi over 4 or 45 degrees, oh, I lied. I messed up. Can anybody help me? Cool, I'll help myself. I meant to call that square root of 2 over 2. So my x coordinate at an angle of 45 degrees is square root of 2 over 2, and my y coordinate is also a square root of 2 over 2. If we move to a different angle. And I look at those other two angles that we used in previous problems. I'm going to have pi over 6 as another triangle on here, and pi over 3 is my last one. So this guy's pi over 6, and this biggest angle here is pi over 3. Now thinking about those as coordinates on a unit circle, for pi over 6, my x coordinate here is square root of 3 over 2, and my y coordinate is 1/2. That pi over 6 triangle and the pi over 3 triangle, they're really kind of the same triangle if we could just like rotate and flip and bend our head around the other side of the board. So we flip those x and y coordinates. And this is a 1/2, and this is a square root of 3 over 2. In each of the other quadrants, these coordinates are essentially staying the same. We're just reflecting them over one axis or the other. So the values aren't really changing. It's just the signs and whether they're positive or negative. We could spend another week talking about the unit circle, but honestly, we don't need to. We're not going like so in depth in the trig in calculus. The bottom line is you need to memorize all of the trig values for our special angles, or you need to be able to quickly read them off of a chart if you're being allowed to use notes on a quiz or a midterm. I think about this as if we're converting units or doing stoichiometry or something. If I have 60 degrees and I want to write that in terms of radians, I'm going to multiply. Right now, I have units of degrees, so I need to multiply by something with units of degrees in the denominator so that my degrees will cancel out, and with units of radians on the top. And so this can be any ratio that's equivalent to 1. And the ratio that I use is pi radians is equivalent to 180 degrees. So this is how I would convert from degrees to radians. So that would turn into, the degrees would cancel out. I'd have 60 pi divided by 180 radians, which I could simplify to pi over 3 radians. If I had to go back the other way, let's say I had 5 pi over 6 radians, and I need to convert that to degrees. I'm going to multiply by a ratio that's equivalent to 1. Because I need those radians to cancel out, I'm going to put radians in the denominator. And I want degrees, so I'm going to put degrees in the numerator. And now I need to have a ratio that matches equivalently. So 180 degrees is the same as pi radians. At this point, my radians would cancel out, my pi's would cancel out. 180 degrees divided by 6 would be 30. So I'd have 30 degrees, and then times that 5 would give me 150 degrees. So let's say that I was looking at this and I'm trying to solve on 0 to 2 pi. That means that I cannot include the negative answer, even though it's a coterminal angle, because this is specifying that whatever angle I'm going to report, it should be between 0 and 2 pi. So that's an example of why a coterminal angle would not be a correct answer in the context of how a question was asked. But if I asked this and I wanted an answer on negative pi to pi, now this is perhaps going to specify a different value that I'm looking for, right? So again, I might think about what that answer is, but I might need a co-terminal answer to be on the window that a problem has given us. Okay, double angle formulas. So if I'm going to get through this problem, oh, maybe I don't even need a double angle formula for this. This was boring. That's okay. We'll do it anyway. I have two things. They're already factored, I just realized, because it's sine of theta times cosine of 2 theta. And so making this equal to 0, I either need sine of theta to be equal to 0 or cosine of 2 theta to be equal to 0. This wasn't really what I meant to do, but we'll do it super quick. If sine of theta is equal to 0, and I'm on 0 to 2 pi inclusive of both, then the angles where sine is equal to 0 are 0, pi, and 2 pi. You can think about that from a unit circle. You can think about that from having memorized a chart, or you can think about it from a graph of sine of x, where I'm going to hit zeros at 0, pi, and 2 pi. For cosine of 2 theta being equal to 0, we have a choice. We can either use an identity for cosine of 2 theta. We can use some kind of double angle identity, but we don't actually need to, because we just have to think about, if I were to rewrite this to say cosine of x is equal to 0, then I know what those x values have to be, pi over 2 and 3 pi over 2. Again, because you're either going to memorize a chart, memorize the unit circle, or memorize what a graph of cosine looks like, where it hits those zeros at pi over 2 and 3 pi over 2. These aren't the answers that we're looking for, however, because I've essentially made a substitution that x is equal to 2 theta. And if I'm trying to answer what theta is equal to, then the theta that I would have to plug in here in order for x to turn into pi over 2 would actually be pi over 4. And in order for this x to be 3 pi over 2, the theta that I would have to plug in here so that 2 times theta was equal to 3 pi over 2 is 3 pi over 4. We're not done, and this is not all of our answers, because now I'm going to modify my picture down here. So if this is actually, if I'm sketching a graph of y is equal to cosine of 2 theta, then that 2 means that my period has been reduced. Instead of completing a full cycle in 2 pi, we complete a full cycle in 2 pi divided by 2, or pi. So that means if I'm looking for all of the values on 0 to 2 pi, I would have to keep going one more cycle. So not only do I have the answers of pi over 4 and 3 pi over 4, but I also need the values over here. I know that the distance between that pi over 4 and this next mystery value we're looking for, this is one full cycle away, which means I need pi over 4 plus an additional pi, which is the period of cosine of 2 theta. So pi over 4 plus another pi is going to give me 5 pi over 4. And if I take that pi, oh, sorry, that wasn't my answer. If I take the 3 pi over 4 and I add one more period to get this next value, 3 pi over 4 plus pi is going to bring me to 7 pi over 4. So my answer to this question would be all of these values and all of those. all of those are solutions to this question. So I really was, this isn't where I thought I was going with it, but it's a good thing we did it. So if we are solving something that has one of these double angles, or if this had been cosine of 3 theta, then we need to think about all of our solutions between 0 to 2 pi by adjusting the period and adding 1 period to each of our values until we get all the way through the interval that we've been given. Or straightforward anyway. The first thing we try with any limit problem, whether we've got trig functions or logs or x's raised to powers, no matter what we're doing, first thing I'm going to try is to just plug the number in. So if I plug in pi over 2, then on top I end up with 1 minus, now cosine of pi over 2, again, that's a value we have to get memorized. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Nothing at all interesting happened with this limit because we were going to pi over 2. So now let's do a more interesting limit. Suppose instead I was taking the limit as x approaches pi of 1 plus cosine x over sine of x. First thing we try with the limit problem is always to plug it in. So if I plug this in, cosine of pi is equal to -1. Again, that's a value that we're going to memorize either from the unit circle or a chart or thinking about the graph of cosine or some other cool way that in your breakout room someone taught you. If I plug in the pi here, sine of pi is 0, which means that we're into a 0 over 0 indeterminate form. Now, if we have x's raised to powers, I usually say we get through this by doing algebra. In this case, we can't get through it doing algebra. We're going to have to get through it doing some kind of trig magic. Now, the trig magic that I'm looking for, most of our trig identities that involve sine, cosine, tangent, secant, cosecant, a lot of those trig identities are with things that are squared. In fact, our sort of fundamental trig identity is that cosine squared theta plus sine squared theta is equal to 1. And you can assume that no one will ever give you this trig identity on any exam ever. You must memorize it. Other trig identities, maybe someone's going to give you on a test. This one, no. This being kind of our fundamental trig identity and things being squared, when I look at this limit problem, I'm thinking to myself, how do I create some things that are going to get squared in here? If I square the top and square the bottom, I have changed the problem, right? If the answer to this limit were 3 over 2, it's not. But if the answer to some limit were 3 over 2, and I had squared the top and squared the bottom, I would end up with 9/4. These are not the same. So I can't just square the top and the bottom to get something squared. But what I can do is multiply the entire fraction creatively by 1. And that multiplying creatively by 1 is going to look like multiplying by 1 minus cosine x over 1 minus cosine x. Now there's something kind of subtle here, and that is in terms of the 2 zeros that we got for the limit, the one on the top isn't a problem, but the one on the bottom is. That's how I know that I want this sine of x term, Pete, I want the sine of x term to cancel out. So whatever I'm going to do to manipulate this, I have to try to change the top because I need to try to make the top something that'll cancel out with that sign in the denominator. Okay, if we keep rolling here, I've got the limit as x approaches pi. So in my numerator, when I distribute that out, because One's plus and one's minus. I know those middle terms are going to cancel. So 1 times 1 is going to give me a 1. Cosine x times negative cosine x is going to be a negative cosine squared x. In the denominator, I still got that sine of x term, but I've also got 1 minus cosine x. And I'm not going to distribute that out. I don't really need that parentheses over there. I'm not going to distribute that out because I'm hoping that the sine of x will cancel. Well, at this point, I'm going to look at my numerator and say, oh, hey, that's kind of neat. This is a manipulation of this identity. So if I subtract cosine squared from both sides, sine squared theta is equal to 1 minus cosine squared theta. So I can replace that 1 minus cosine squared theta on top, or 1 minus cosine squared x, and I can turn this into the limit as x approaches pi of sine squared x over sine x times 1 minus cosine x. Now, remembering that this notation of sine squared x, that's how we read it, really means that I have sine of x, whole thing squared. So one of those signs will cancel out, and I'm going to be left with the limit as x approaches pi. I've got a sine of x left on the top, and in the denominator, I've got 1 minus cosine x. Last but not least, I'm ready to plug in that limit. So if I plug in the pi, sine of pi, well, that's equal to 0. But as long as I don't get 0 in the denominator, it's okay. When I plug in pi here, cosine of pi is -1. So I have 1 minus -1, which means I have 0 over 2, which is 0. And that is the answer to our original limit.